Okay, fine. So now let us come to the main topic which I want to discuss in today's lecture. Firstly, let us understand why simulation. Why do we want to go towards the simulation route? And to motivate this lecture, I am going to take an example from a NeurIPS behavior challenge. This challenge was released last year, and let's understand what this challenge is all about. On the left, you can see that they have a demo gallery which has a lot of tasks which start from task 0 and they go all the way up to task 49. Now let's look at task 0 and see what it is. The name of the task is turn on the radio receiver that's on the table in the living room. You can see we have a living room. Now all of this is in the simulation. It's not real. And you can see there is a radio in the middle. Now we have to train a robot to pick this radio up and to press the on button, just as you can see in the screen right now. The arm is moving, it is picking the radio up and it's pressing that red button. This is one task. Let's look at another task, which is, let's say, cleaning up plates and food. So the duration of this task is pretty long, 7 minutes 37 seconds on average. And from the breakfast table in the kitchen, move both pizzas, keeping each on its plate, into the same refrigerator. Put both the bowls in the sink and make sure the refrigerator is closed. Let's see. Is there a way to, yeah, I'll maybe increase the speed to 2x. And so I think the first thing the robot will do is move both pizzas, keeping each on its plate. Let's see what it does. So keeping the first pizza, then it keeps the second pizza also. And then it has to close the fridge and put the bowls in the sink. Okay, so like this, there are a lot of tasks. As you can see on the left hand side, they have around 14, total 50 tasks. And what is this behavior challenge? Let's see. Okay, so the idea is to solve all of these 50 full length household tasks, and they already have a lot of data available, which is done using teleoperation. They have already provided so much data of robots moving around and completing these tasks. What is the challenge about? We have to take all these tasks as input and we have to train a policy which learns to generalize using these tasks. And this is one example, but the reason I'm showing this right now is simulation allows us to try out changes in the policy architecture and understand whether they work or not. So it allows a room for a lot of trial and error before we zero in on the correct policy or the correct possible set of policies. And the winner of this challenge, he has released a video on YouTube. I encourage all of you to take a look at this 90-minute video. It is extremely enlightening. I learned a lot of stuff when I saw this video. And this person is very active in the field of robotics. His name is Ilya, and they got the first prize in this competition. So they used a vision language action model, Pi Zero, but
most people over 40 will enter 2026 still using ChatGPT like Google. Don't.
Yeah, so they did not just directly use Pi 0.5 off the shelf. but they made a lot of changes to the policy and made it work for this specific simulation scenario. Now, this is the same reason why I've been emphasizing so much on the theory behind policies, because unless you know how the policy is developed, you will not know what changes, what architectural changes to make within the policy. So they made a lot of changes. I think they made around 3 to 4 changes in the policy architecture and made it work. So essentially, they took a VLA, which is Pi 0.5, changed the architecture, and trained it on these. They didn't use all these 50 tasks. I think they trained it on slightly less, but they got the first prize. So I encourage all of you to look at this so that you understand the power of simulation and how it allows us to try out different variations in the policy architecture and learn from them. Okay, so this is the first thing. Now, when we come to simulation, what are the different simulation options that we have at our disposal? There is a nice table which I want to show to all of you. There are a number of options in of simulation environments. So here they have listed down 7 options. The first is Maniskill 3. Then we have ISAC Lab, then RoboCasa, RL Bench, Omni Gibson, Habitat, and AI2 Thor. Out of these, I would say ISAC Lab is the most popular, which we see people use a lot. But I found it slightly hard to directly deep dive into, and I found Maniskill to be the most convenient to get started with simulating policies in a environment. Now, if you look at all the features which these environments offer, so Maniskill is, at least that's what they claim in their paper, that it is supposedly the best among all the environments, even though if you rank them in the order of popularity, ISAC Lab would be the top. But one of the main advantages of Maniskill is, I would say, the parallel simulation and parallelized rendering, which I will show some examples of. And I think for people who are getting into robotics and starting simulation, Maniskill and ISAC Lab should be the two go-to options to start learning how to simulate policies in virtual environments. So today the lecture will be completely focused on Maniskill 3, where I will be explaining all of you how to use this environment and how do we simulate policies. Now, what will be the final goal of today's lecture? Up until now, what we have done is we have collected real data sets of of pick and place, right? And we have trained a manipulator arm on the recorded data set using the act policy. And the whole objective was to for the policy to learn how to pick and place objects and maybe generalize well on unseen data. Now, our final goal today will be very similar. We are going to collect demonstrations of pick and place in the simulation environment, and we are going to train a manipulator arm on the recorded dataset using the ACT policy. Everything will happen inside the simulation. Now, a last step, the ultimate step of why we do simulation is finally we have to do sim to real. Whatever we are doing in the simulation, we have to transfer to real. And that is a bit challenging. There are some uh, blogs and there are some articles available where people are showing how to do sim to real, but it's significantly challenging. I will touch upon that briefly towards the end of the lecture also, but the main objective of today's lecture is to teach you how to implement policies in the Maniskill environment and understand or test out various policies and figure out which one is performing the best. So today we'll be doing not just imitation learning, we'll be doing reinforcement learning also. Some of you might not be familiar with RL, but RL as a field is very intuitive. It is very similar to how humans think. So I think all of you will be able to grasp it easily. Now, the way I got introduced to Maniskill was when I looked at this podcast. So here, uh, the name of this channel is Robo Papers, And both of these guys at the top, they are the ones who are the hosts, and they invite a lot of different people. I found these discussions to be very grounded, very technical, from the foundations, and I really like listening to them. It's not a very popular channel, but I recommend this channel to everyone who wants to understand what new things are coming up in the field of robotics. So they had invited Stone Tao, one of the creators of Maniskill 3. And when I heard him, the intentions behind Maniskill and what kind of features it offers, I was impressed and I immediately wanted to try it out. So I would recommend all of you to look at this podcast also and understand the motivations behind Maniskill, what all features it has, what all stuff we can do with it, etc. Okay, now this is the main Maniskill documentation. They have listed down a lot of tasks, examples, baselines, and if you go to user guide, you will see a lot of stuff here. And for us today, we'll be looking at on the left. You see there they have a section called learning from demonstrations, and within this they have a section called baselines. Now, if you go in the baselines, you see they have standard behavior cloning, diffusion policy, and ACT. Now, why these baselines have been given is if you want to develop a policy which is different than ACT, which is better, similar to what we were discussing in the last lecture, and you want to try out a lot of stuff and compare it with the baseline, you can do so in the environment itself. So they have already given the code for the baseline. You can take this code as the baseline, update your code and compare the results of both the codes, the baseline code and whatever architectural changes you have made. I think it's a good practice for all of us to learn how to make tweaks in the architecture to get improvements in the output. So that's why they have given these baselines. Okay, so we will be learning examples from this documentation, and initially I will start by following a Google Colab notebook, which they have shared in the documentation. Let me share this notebook with all of you. Okay, please have a look at this link and keep it open on the side. Now, before we start explaining about Maniskill environment, I want to talk about another environment which is called as Gymnasium. How many of you have heard about the Gymnasium environment or used it before? Can you type in the chat? Okay, Vishnu has used it. Vishaka says she has not. Rajesh has used Mujoko. Paresh has used it. Okay, I think many of you have not used the OpenAI Gymnasium. So I've written an article on this in our Substack. I will share this link with you. This is also a good introduction to RL. You can open this up as I'm going through the Gymnasium. Okay, so first of all, Gymnasium was an environment initially released by OpenAI, but now it is no longer maintained by OpenAI. It is maintained by, I think, Farama. So it's a name of a community which is maintaining it. So the OpenAI name is no longer associated with Gymnasium currently. So this was a Python library which was developed in the year 2017. And the main goal of Gymnasium is to provide a rich collection of RL experiments using a unified interface. So basically, it makes programming of reinforcement learning very, very easy and straightforward. The reason I'm talking about Gymnasium environment right now is Maniskill is built on top of the Gymnasium environments. So you will see a lot of parallels between the commands which we use in Gymnasium and the commands which are used in the uh, Maniskill documentation. So initially, I'm going to do a brief overview of the main commands in the Gymnasium environment so that all of us are at least familiar with the uh, commands which are used in the Maniskill environment repeatedly. Okay, so let's look at this diagram. Gymnasium, at the heart of it, it has two spaces. it has the action space, and it has the environment space. Now, to understand these terminologies, we need to first briefly dive deep into what is observations and actions from a reinforcement learning point of view. So imagine that you have an agent. Okay, let's imagine you have a lunar lander. So the lunar lander, have I given a, yeah. So the lunar lander looks like this, and we are trying to land it on let's say the surface of a planet. Let's say we are trying to land it on moon. Now, what happens is that this agent, this is the agent, and the environment it's interacting with is the sky. Now, the agent is going to take certain actions. Uh, what are the actions which the agent is going to take? The agent is either going to move left, right, up, or down. Depending on the actions, the agent is going to receive some observations and rewards from the environment. Based on that, it is again going to take the next action. Again, it is going to receive some set of observations, and similarly, it's going to go in this loop. Now, an example of this, which is all of us have, I think, seen is, let's say we are learning to ride a bicycle. So we are the agent here, and we are interacting with the environment. So we take an action. Let's say we put our feet in the pedal, we press the pedal hard, and let's say the bicycle tilts, it goes off balance. We receive a set of observation from the environment, and we receive a negative reward, which tells us that okay, maybe I need to correct my trajectory. I take another action, I receive again a new set of observations from the environment. So in the reinforcement learning terminology, there are three words which are very commonly used, which are states, actions, and rewards. State is nothing but the current observations which I am receiving from my environment. Action is whatever I am doing based on those observations. Let's say you are playing the game of chess. Now, in that example, the state is the current configuration of the chess pieces on the board. The action is which piece you are moving on the chessboard. And what is the reward? In the case of chess, the reward is zero for all the time steps. Until the last time, whether we win or lose, we get a reward of +1 or -1, let's say. So that is an example of a case where we have sparse rewards. In many cases, you have sparse rewards. In some cases, you have dense rewards as well. But then we have observations, actions, and rewards. That is the key thing which I might use this terminology repeatedly in today's lecture. So I wanted to explain this to all of you. Now, Gymnasium has two spaces, the action space and the environment space. So let's take an example of this lunar lander. It's there in their official documentation. I will share this link in the chat. Now, when you go to this link, at the top you can see it starts with the action space, and it's written discrete into bracket 4, which means that there are four distinct actions which the lunar lander is supposed to take. Now, what are the four distinct actions? 0, 1, 2, and 3. 0 means do nothing. 1 means fire left orientation engine. 2 means fire main engine, and 3 means fire the right orientation engine. So there are four possible actions which are available to the lunar lander. Now, what is the observation space? Let's have a look at it. The observation space is a 8-dimensional vector, which is the coordinates of the lander in x and y, the linear velocities in x and y, the angle, the angular velocity, and two booleans which represent whether each leg is in contact with the ground or not. So the action space is discrete 4. Now you see this weird looking thing in the observation space which says box and there are a lot of numbers. So let's understand what this is. First, let's look at this first array. So this first array consists of 1, 2, 3, 4, 5, 6, 7, 8. 8 numbers because all of these numbers represent something specific. And minus 2.5 is the minimum range of what is the first observation? Coordinate in the x direction. So the x coordinate has a minimum value of minus 2.5. The y coordinate has a minimum value of minus 2.5. What is the third observation over here? Linear velocity in the x has a minimum value of minus 10. So this is what these 8 numbers represent. Now, what is this second array? The second array is the maximum. So essentially, we are getting the range here for all the observation values. This is the minimum and this is the maximum. And 8 simply means there are 8 numbers, and float 32 is the type of these numbers. Okay, and you see here, they have something gymnasium.make. Now, when you write this command in Python, it will instantiate the lunar lander environment. It is that simple to instantiate it. That is why people initially got so fascinated with Gymnasium, because it included a lot of environments like this. In fact, we can create our own custom environments also in Gymnasium. And then that is the first step. You create an environment, you define the action space, and you define the observation space. Now, the question you might be having is that, okay, fine, all of this is defined. How do I control my agent according to some specific policy? So, okay, one thing I did not explain is what are the rewards. So, here the reward is plus 100 for landing safely, minus 100 for crashing. Reward is increased by 10 points for each leg that is in contact with the ground. It is decreased by 0.03 each frame a side engine is firing. And there are some conditions which are defined for the rewards. Now I think you can understand this agent environment interface very nicely. The agent will receive 8 observations, which are the coordinates, the angular velocities, whether the leg is in touch with the ground or not. Based on that, it will take an action. Let's say it's very close to the surface. If that is the case, then the agent will probably fire in the downward direction so that it's going down. If it's very close, it will do nothing. It will rest on the surface. So the actions are largely dependent on where I am on the surface. And how is it receiving that information? It is captured in the state. And at every single timestamp, the agent is receiving some reward from the environment. So initially, if it's very far from the surface, probably the rewards are very less. But as it goes close to the surface, if it crashes, suddenly you get a huge negative reward. And the policy you should construct should be such that if it gets a very negative reward, we should tell our agent that, okay, whatever actions you have taken in the past for all those state observations should not be taken in the future. Learn from this and take better actions next time. So this is the agent environment interface, which is created in the Gymnasium environment very easily using one simple line. Now, what we'll do is let us look at our first code to create a sample of the observation and action spaces. So why don't all of you head over to VS Code and we can try this out. So this is the first command you need, pip install Gymnasium. I have probably already installed it, but let me open up a new okay, I have created a folder called RL over here, and there I'm going to create first script.py. Okay, so now what I'll do is I'll copy this and paste it over here. Let's look at this code. So I have written import Gymnasium as gym. Then we have the gym.make, which I explained before. I'll change this version to v2. I think v3 is no longer operational. Then we take an action. So for that, the command is env dot action underscore space dot sample. So what this will do is it will sample a random action from the action space, which we already know it's either 0, 1, 2, or 3. And this will sample a random observation from the observation space. Okay, and then we are just printing the action space and the observation space. So let's run this. I hope all of you are trying this out as we speak. Okay, so we have got the answer now. Here you can see the sample action from action space is 0. Sample observation, it must have picked 8 observations. 1, 2, 3, 4, 5, 6, 7, 8. Okay, makes sense. Action space is discrete 4 and observation space is box with the minimum range, minimum and maximum, 8 numbers and float 32. This is exactly what we expected. Preetham is asking, is there a readme to follow? So we are just trying to understand the gymnasium environment, which forms the basis for our Maniskill explanation. And we are explaining the basics of the commands in the gymnasium environment, which are used to define the agent environment interface. So you have not missed out on much. You can directly start from this piece of code and you can run it in Python. Now, have all of you understood this part? Can you message in the chat if I'm going too fast or is the speed good enough for you to understand? Okay, I think Pramod, Vishnu, Paresh, Uday, Rajesh, all of you seem to be following up until now. Now let's go ahead to the next part where we'll actually uh, try to take actions. Lunar lander V2 is giving depreciation error. Hmm. It might give some warning, but I think it should work. At least it did in my case. Initially, I was using V3. This was around 3 months back, but for V3, I got an error saying that it's no longer operational. So I changed it to V2 and then it worked for me. I think it depends on the Gymnasium environment which you have downloaded. Maybe you can use V3 and see. I think that might work. Yeah, I think, yeah, I mean, it depends on your gym environment. I think you should use V3 in this case. Okay, so let's move ahead. Just to revise, the gym.make function creates the environment for us. The observation space dot sample samples an observation from the observation space. The action space dot samples an action from the action space. Uh, okay, so here I have mentioned you might think that I have never defined the action and observation space, but they are defined in the environment for you. This is one of the advantages of using the gymnasium environment. So far, we have just created the agent and the environment interface. We have not understood how to control our lunar lander. To do that, it's very simple. I am going to run another code over here. Here you can see that again we are creating the same environment gym.make, and this time the difference though is I've used two more functions. The first is env.reset, then we have env.render, and the most important function here is the env.step. Now, what the env.step does is very interesting. The env.step takes an action in the environment. Now, here you can see I'm taking a random action. Ideally, the action should be dependent on the observations, right? But I'm taking a random step in the environment. Then I'm receiving one more action. Then I'm again taking a random step. This is happening 200 times. So when I run this code, I will see my lunar lander moving and take completely random steps for each observation. And what this env.step does is it takes an action as an input and it gives the observation and the reward as an output. So Let's run this so that you understand what I'm talking about. Copy this and paste it over here, and let's run it now. The env.render simply means that we are going to render it in the form of a video. Okay, it says environment v3 does not exist, so I'll change to v2 and check it. You see, my lander is somewhere at the top and it will crash. Yeah, it's not a smooth landing. And the reason the landing was not smooth because I'm taking random actions for every observation. Let me run this again and see what happens. Every time you'll get a different video because we are taking here you can see it slowly descends. This was better, but still it's not the best, and in many cases it actually crashes. Now, why is this working and why am I getting a trajectory? Let's understand this. The first step is, of course, the creation of the environment using the gym.make function. We have used another function called env.reset, which is used to reset the episode for all the tasks. Now, as I said, the most important function here is the env.step. It takes the action as an input and gives the following as the output. Observation, which represents the agent observation of the environment. Second is the reward, the amount of reward received as a result of taking this action. Remember, we have already defined the reward, so we have the rewards accessible to us depending on the actions which are taken by the agent at every observation. Then it gives two more flags. The first flag is terminated or not, which is a boolean indicating whether the terminal state has been reached or not. The truncated flag is really useless. I have not found any use of this. As I have explained here, I have not understood this requirement. And second is an info, which is again a dictionary containing some diagnostic information. But for us, the most important is the observation and the reward. And now you can see here this agent environment loop. We are getting this loop because of the env.step function, because it's taking an action as an input and giving the state and the reward as an output. So because of this env.step function, we are creating this loop successfully. Okay, so after you run this code, you will see a pygame window open with the lunar rover lander. Now, in this example, we have taken a very uh, simple way out that we are taking random actions. In reality, the actions should be always conditioned or dependent on the observations, and there should be a specific policy. So here I have mentioned that this is not very good. If only it was this easy to run RL problems. The reason it is not this easy is because we have to define a policy, which currently we are not going to focus on. But what people generally do is that they develop policies such that whenever you are getting good rewards at the end of the trajectory, then you upweight all the actions which are taken in the trajectory. If you get a very bad reward, then for the observations which are encountered in that trajectory, you tell your agent that don't take these specific actions which you have taken because you have got very bad reward. And there are a lot of algorithms people use. One of the most common algorithms is called proximal policy optimization, PPO. PPO and some of its variants are very common in the field of robotics. Okay, so are there any questions in the first part of today's lecture, which was about Gymnasium and the different commands which are used in the Gymnasium environment?
Just one question, Dr. Rajat. I did not understand this sparse reward and
Okay, okay, okay. So let's take an example. Uh, let's take the game of chess itself. We are playing a lot of moves, right? In the game of chess, maybe 100, 150 moves.
Hmm.
And there is no way to for us to understand whether every individual step, how valuable was each of my move. I am only getting a single signal at the end of these 150 moves, whether I won the game or I lose the game.
Okay.
Now, this is one of the biggest issues with RL is the inefficiency of the reward signal. Only after 150 plays, I'm getting a reward, which is
Hmm.
not very efficient, right? Similarly, same thing happens with a large language model. Uh,
Hmm.
when you fine tune an LLM using reinforcement learning, you get the reward only after the entire answer is completed. Let's say I ask the question, what is 2 plus 2?
Hmm.
And the model responds, the output of 2 plus 2 is 4. Only after the response or the answer is completed, I get a reward. Okay, this answer is correct. I'll give a positive reward and I will reinforce all the tokens which I have seen in the trajectory before. Now, this is very inefficient. What happens in reality is, let's say, I am doing some task. Humans get instantaneous reward from so many things, right? Like, let's say you're playing a sport, and let's say you're playing basketball, you're dribbling the ball, you're passing it. And every single time, there are your nerves are giving you some sort of signals that, okay, this was correct, this was wrong, you should not do this was not received well. But somehow the way RL problems have been tackled by the community so far is completely different from how humans perceive the world. Humans don't complete a task and after that they get a reward and they think back, oh, okay, I did this 100 steps and now I'll do all these steps again. But we
Hmm.
get signals at every individual time steps that we are following.
Hmm.
So there is an alternative track where you try to give rewards for the process also. Don't just give rewards for the output. So that's why there are two different categories of reward models, which are outcome based rewards or process based rewards. And largely what we are seeing here is this is completely outcome based reward, whether the lander is landing correctly or not. I'm not giving rewards for the individual moves which the lander is making in the trajectory.
Correct.
So that is the sparse reward problem in the field of reinforcement learning.
Right. And dense rewards is at every process step also we give some.
Yes, exactly. At every time step, we receive a response from the model.
Okay. Okay. Understood. Thank you.
Yeah. Rajesh has asked a
Sir, one
question. Are we
question.
going to define the policy in this session? Yes, we are going to define a policy. We will do that in the Maniskill environment though. So I will explain how to define a PPO policy in Maniskill.
So this virtual environment, right? We can only use for RL, right? Other than RL, we can't. We won't be using.
We can use it for RL and we can use it for imitation learning also. So I'll show both the examples in today's class.
Okay. And sir, one more exam. One more question. So
Mhm.
exactly, exact point of falling, right? Or in this specific example, uh, at uh, which axis, say X, Y, Z coordinates, right? If I want
Mhm.
to correctly map that thing, right, is it possible to map here by using virtual environment?
Yes. So here it's actually mapping the exact points because at every time step it is tracking the XY coordinates of the lunar lander. So even though we are not seeing it in the picture, you can imagine a coordinate axis attached to the body of the lander, and the axis is not just translating but it is rotating also. So we have a track of the XY coordinates, the angle, and also the angular velocity. Everything is tracked, and only based on that an action is taken.
Ah, okay. So that means we have accuracy. Yeah. So I thought
Yeah,
it's
yeah,
like,
definitely. Yes.
okay. Thank you.
The accuracy, those aspects are slightly abstracted over here in the gymnasium environment because they wanted to make something which is like plug and play. You have these custom 100 environments. You just use gym.make and load that custom environment and customize your policy, input a policy in that environment. Now, what type of policies people input? You can either have policies which are based on just value functions, which is called as Q learning, or you can have policies which are based on policy gradient methods, which are either vanilla policy gradient or PPO. Today, we are going to look at an example of a proximal policy optimization, which is the PPO method, which also comes under policy gradient class of methods. Okay, so let's do one thing. We'll take a small break of 2 minutes because I think all of us should just reset our minds in 2 minutes, and then we will move to the Maniskill environment and we'll understand how that works. So I will just take a pause for 2 minutes and then I will be back. Okay, let us get started now with the second part of today's lecture. I'll quickly begin sharing my screen and okay, so in the next part, all of us are going to open this Google Colab notebook which I've shared in the chat. Let me just share it again. And we will run all these individual cells now in a step-by-step manner. So this notebook is a perfect demonstration of Maniskill environment, how it is built on top of Gymnasium and the different applications using the Maniskill environment. So first I'll just connect this. Okay, so here it says to begin prepare the Colab environment by switching to a GPU environment. So I think all of us have access to these T4 GPUs. So you can change your runtime to runtime type. Instead of using CPU, you can use these GPUs. If you have A100, you can use that also over here. Then you can start running these cells where you can install Maniskill and Tyro.
Do we need to wait for each cell to finish before we click the next one?
Yes, yes. Unless this runs, you will not be able to run the next one. At least the setup code should, yeah, I think it's ready now. So these two have run. Now we can move to the next ones. Okay, now here what we are going to do is, you see it says Maniskill follows the OpenAI Gym API, making it compatible with a wide range of libraries like those which are used in reinforcement learning. And there is an option of CPU simulation here first. So we will see what happens in GPU simulation also, but here during CPU simulation, the API is followed completely, and you can see why it is followed completely. So the first thing is again we are doing gym.make, the same command which we used in for the lunar lander case. Then we do env.reset like we did before, and you can see here they are also taking random steps, env.step, and there is a random action being taken from the action space. And as I mentioned, there are five things given as an output from the env.step. We get either the observation, we get the reward, we get these flags terminated or truncated, and we get info. So the output will be the info.item, which is, I'll show you what it says. And then we are calculating the number of frames per second also. So just run this cell so that it will import the uh, Gymnasium environment peg insertion side. We will look at what this environment also means. And here you can see it is using one parallel environment. Later we will use multiple parallel environments as well. And the observation mode is state. Control mode is the joint delta position. So what this means is that you have two options in the control mode. You can either control the joints of the arm, or you can just control the end effector. So the end effector is the location of the end effector is finally going to be dependent on the location of all the individual joints. Let's say you take an example of the SO101 arm. The SO101 arm has 6 degrees of freedom. So either you can control these 6 joints separately or individually, or the second option is that you can just control the end effector, which is the gripper. So here we are using the control mode, which is the joint delta positions. And the observation space is minus infinity to infinity. This is the range of the observation space, 1 comma 43, and the action space is, there are 8 possible actions here. We can take a look at what all these actions are, but for now let's just run these different cells and try to understand broadly how to integrate policies within the Maniskill environment. Okay, so now in the next step, what they have done is uh, they have wrapped a CPU wrapper around this. So this will not be required later when we are using GPUs, but this is something which is required if you are running this on a single CPU. And later you can see if you run the next piece of code, what does the, okay, so it says can't convert. I think here what we are doing is this is meant for a CPU and we are running it on a GPU. So that's why we are getting a mismatch. Yeah, if you do dot CPU over here, I think it will run fine, as you can see here. Yeah, dot CPU after 0. So Vishnu also recommended the same. So now what the peg insertion task is, we have to take this peg and we have to insert it in this hole over here. And you can see this manipulator arm. This is the manipulator arm which is now available in the environment with us along with the rest of the objects. Now this is something which Maniskill has built on top of OpenAI Gymnasium. For example, in Gymnasium, you won't have this arm present in the simulation environment. But in Maniskill, we, along with the other objects, we also can simulate this robotic arm, as you see in this figure. Now, in the next step, we are trying to understand how we can simulate multiple environments in parallel. Here, what we did was we only did gym.make this, and there was one single environment. Now, in the next step, we are going to simulate 2048 environments in parallel. And in all these environments, we are going to take a step and perform random actions. So let's run this piece of cell. And here it gives an error. And the reason it gives an error is because uh, we are first running this piece of cell and then we are running this piece of cell. So it says that if you want to run this independently, you can simply restart the notebook. So there is a good question on the chat whether the observations also include visual input over here. So I will explain that. Here, if you look at the observations, it does include RGBD, which is the visual inputs also. There is a camera which is placed in the environment by default. But there is an option of in Maniskill to have only the states or the states plus the observations. So we are going to look at both the examples shortly when we implement the ACT policy. So now for now, what we have to do is we have to restart the environment. Restart and again run this setup code. Now we will not run this piece of cell. We will directly go down and we will run this. So I hope you are understanding the implication of this 2048. What this 2048 means is that let's say you want to simulate any policy. Let's say you want to train an agent using reinforcement learning. And initially you just have one environment. So the agent takes actions and learns from it. Now, instead of that, imagine you have 2000 parallel environments where the robot is taking actions and learning from it. That will save up computational cost by a huge order of magnitude. And this is exactly what it says over here, that test task ID pickup pick cube v1 2048 parallel environments. Observation mode is state. Yeah, so this observation mode is state. So actually it's not capturing the observations which was asked before. There is another observation mode which is state plus observations where we do capture the observations as well. By default, what Maniskill does is it does not capture the images which are there in the environment. So it is only the robot state which is captured. It does not capture the images. Uh, we will understand how to modify the data so that you have the joint states plus the observations from the cameras. So Vishwa is asking how is computational cost reduced? Yeah, so since you're simulating a lot of trajectories in the same amount of time, uh, you can reduce the your training time significantly if you're using all these environments and it is simulating the policy in parallel on all the environments in a single run. So if you look at this graph, that was one of the advantages of Maniskill 3, which is parallelized simulation. There is also parallelized rendering, but right now what we have looked at is this first point, which is parallelized simulation, where it is running this policy on 2048 environments in parallel. Here, there is no policy being run. It is simply taking random actions as you see over here. So it's randomly. So we have a pick cube task, but at it might not even pick the cube. It is probably moving in space in whatever way it can. But the final goal is to have a logic and not just give a random action in this env dot step. So this is how Maniskill builds on top of the Gymnasium environment so that you have a manipulator arm now sitting inside your environment. And not just you have a manipulator arm, you have these predefined environments and tasks like insert peg, picking cube. And we are going to use this same task today, which is picking cube, and we are going to train it using the ACT policy. That is our final goal in today's lecture. Okay, now the next thing is state plus visual. So it says that uh, Maniskill is able to render in parallel, allowing for extremely high frame per second for visual rendering, which can be incredibly useful for computer vision workflows and visual RL. So let's run this and see over here. Here you can see the observation mode I have defined as RGBD. Now, the moment this is defined, it means that it is capturing not just the state of the robot, but it is capturing also the images which have been recorded by the camera. At every single time step, this is captured. Let's run this code and see. Everything else is the same. If you see, this loop is the same. We are looping in a random action at every time step. The only difference we have made here is that we have changed the observation mode to RGBD and we have reduced the number of environments to 512. So here you can see it is 5 and 12 environments in parallel. The observation mode is RGBD. The control mode is still the joint delta positions, which is fine. And these are the sensor details. So it is capturing 128 by 128 pixels at every time step. Simulation frequency, control frequency. This is the observation space and this is the action space. Now the action space is 8. The reason it is 8 is because the arm which we have considered has 8 degrees of freedom. We have to look exactly how the 2 additional degrees of freedom are coming from compared to the SO101 arm. But my guess is that the gripper not just there might be one more degree of freedom in the gripper, I think, which makes it 7, and the 8 one is something we have to check. But most probably the arm which they simulate over here is this Franca Panda arm, which is quite common. And this has, if you look at the degree of freedom of this, okay, this is 7 degree of freedom. So we have to check where the 8th degree of freedom is coming from. Okay, so this is something which is pending. We have to look at it closely. And yeah, I think the rest of the things should be fine. Now you run this cell and you can visualize this. So here, what I'm showing is an observation from the sensor data. And this is what your camera is capturing at every single time step, which I'm showing here right now. So there is a base camera which is set in Maniskill, and that camera is capturing frame at every single time step only if you mention the observation mode as RGBD. So in the baseline, when they have this ACT policy, if you click on this link, uh, they have two options, train.py and train_rgbd.py. So what this train.py does is, if you click on this, I don't think they have, yeah, so they don't capture the images at every time step, but this train_rgbd it does, which is exactly what we want. So we will use this code in our training, not the train.py file. Okay, now we have visualized how the image is captured by the camera at every time step. Um, yeah, so here what it says is you have a lot of flexibility with the environments. So for example, if I just run this, you will see the pick cube environment and how it looks like. So let's see what's happening here. Gym.make is environment ID, which is what we are defining here at the start, pick cube v1. Number of environments are 4. That's why you see 4 screens over here. We are showing the visualization for 4 different environments. The observation mode is RGBD plus segmentation also. The reward mode is dense. Control mode is the joint delta positions. Robot UID is the panda. This was the robot which I was talking about. And enable shadow is true, so it means that uh, we'll see shadows in the images. And the rest of the things, I think there is no step being performed here. It's they are just capturing the images from external cameras at these four different environments. So if you look at what is printed, RGBs dot and RGB is this env dot render RGB array. So let's try to change some of these environments. Let's say stack cube and you run this. So here the objective is to pick one green cube and place it on top of the red cube. If you see pick cube, here the objective is uh, to pick this red cube and place it on top of this green circle. So that is what we are going to train today. It is slightly different than the pick and place which we trained on, but conceptually it is similar. It is picking from one coordinate and it is placing at a second coordinate. Okay, so this is, I think if you run this piece of code, you can visualize the point clouds, the sensor data, base RGB, depth and segmentation. So for ACT policy, we are not going to use the depth that much. We are only going to use RGB. But this is just for your information that it captures the depth and the segmentation details also at every time step. Okay, so we are not going to require this point cloud observation, so I'll not focus on it that much. In the next step, they have shown this function called record episode, which when you click this, you will see one episode will be recorded. Now, this episode is for the pick cube task. And whenever an episode is being recorded, there will be some actions being taken in the environment. And if you look at this env.step, it is taking one action. So there will be a play option over here. So you see it moves randomly over here, and it is designed that way because the actions are taken randomly. Let me play this again. Our objective is to pick this red cube and place it on top of this green sphere. That is the pick and place task which is defined in the Maniskill environment. Now, I hope with all the discussion that we have had so far, you are able to understand this code. First thing you should look for is the gym.make, then the env.reset, and the env.step. These are the three things which 100% should be there in the code whenever we are simulating anything in the gymnasium environment. So the rest of the things are they have added like the record episode and yeah, this is one thing which I had not explained before, but I think this is very self-explanatory what is happening over here.
I mean, we have this sim to real, but in the same way, is there a possibility we can have real to sim in the beginning? We can transfer all our recordings, calibration, etc. to this engine and
Uh,
then get it all trained. But again, sim to sim only. We within the same sim we test everything if it works,
mhm.
and then we can transfer to the real if such a thing exists.
So okay, so I think what people prefer is that if you have simulated real data, then people rather use that real data itself to train a policy on. They don't convert that to simulation data. But because the whole point of using simulation data is you can try out uh, different policies and uh, you can figure out the best parameter combination and then deploy it in the real world. But if you have already collected a lot of demos, then what you're suggesting is that what if we can import those simulations within the Maniskill environment, and we can train a policy using those simulations and then work out the best parameter combination and then again deploy it back to the real.
That way we can save the real motors, in the real life.
Yeah. This is something I have not seen before. Always I have seen sim to real.
Uh,
Real to sim is something which is that even practiced? I'm not really sure about it.
so
Yeah,
I
you're
have
saying
quite
it's a big research area right now.
small full of questions. But if we can record real world things, we
Mm-hmm.
could use that as an imitation data. Like robot is learning through RL, but in the real world data, we could provide some right examples kind of thing. So mix of RL plus imitation.
Yeah.
That
Makes
could
sense.
improve the training speed faster. Like
Yeah,
instead of just doing
sure,
everything
sure,
in
sure.
RL. So
Makes sense. I think if we are able to import these trajectories in the simulation, we can train the initial base policy using imitation learning, and then we can do RL. So I think the starting point will be much better because in RL, that's the biggest problem. It starts randomly. But if we do imitation learning and that is a starting point for RL, then I think that will make a lot of sense. Yeah.
Even right now, people are making digital twins for example, in our company, we are making digital twins for warehouse, and we are trying to put robots also there. So it's like real to sim. We collect the data from the bots and
Uh,
try to have a replica of the real bot in the simulation, so we can see what the throughput can be if we change some parameters. So yeah, it is a thing we will do.
okay.
So yesterday, I visited a, hacker house where they were trying to demonstrate using all this VR, XR basically, trying to do things. So I'm just curious where we, I think it's probably one of you said probably is much closer where imitation learning you can introduce through this XR,
Yeah. Mhm.
and then maybe that is, yeah, cool idea.
It is, I think, because one of the drawbacks of imitation learning is it does not generalize well to unseen scenarios. But if it is trained to self-improve using rewards it's getting from the environment, then I think it will solve that drawback of imitation learning in a way. Sriharsha is saying, let's say we got a good policy that is working in the simulation. Yes, that's one of the biggest challenges in sim to real. So in all of the tutorials which where people teach sim to real, one of the biggest challenge or the hurdle is to make sure your real environment completely aligns with the simulation environment. This means the location of the camera with respect to the location of the robot. That is the first thing. And there is an option like whatever images you are capturing in real world should be exactly the same as the images which are captured in the simulation. And if there is some discrepancy, then the policy is trained on something, but what you see in real world is something completely different. So it's not going to work well in reality. So a lot of care has to be taken to make sure that both these match. I will show one tutorial to you, which was released by Maniskill, where they have trained an SO100 arm in simulation and then transferred it to real, and it works quite well. But it does not work well for SO101, that same tutorial. So that is one open line of work where if we are able to uh, build a code which can transfer the policy from sim to real for SO101, then I think it will be very valuable. But then most of these like behavior challenges and everything that you see, they have nothing with respect to application of sim to real. Their main focus is, okay, can you develop a policy good enough that is working well on all these scenarios? And then we take that policy and we fine tune it on the real data set. I think that is the strategy which people might be using instead of uh, doing sim to real and that going through that route. Paresh is asking, can't we do something like augmentation for the different environment factors to further generalize the policy before sending to real? Uh, I I think always the challenge if we do sim to real, especially if we are doing imitation learning, is imitation learning relies a lot on whatever you have shown in the training. In the testing, is it more or less similar? Then only it will work well. Now imagine you have trained something in simulation and you bring it to real and you are thinking that okay fine, many things look similar, but there will be a lot of small differences. So it might turn out that you have trained for one data set, but in reality the data set is completely different or even partially different. And then it will be like you have trained the robot on X and you want to deploy it on Y. So there will be something which will not work. And but I think in reinforcement learning things will be slightly different because reinforcement learning doesn't completely depend on what you're seeing in the training and imitating that, but it learns from the signals. And I think that is more robust, like learning from signals is more robust to changes in the environment as opposed to learning through imitations. So I would assume that RL training in simulation and transferring that to real would have a better accuracy compared to imitation learning.
Vishnu, if we to use this RL to train, does it work with your SLAM in a new environment? Does it figure out?
Uh, yeah, actually, people do domain randomization. Like if you have a simulation environment, they try that with different parameters. Like if we have, let's say we have a mobile robot and we want to drive it on a surface, they try with different friction surfaces. So yeah, yeah, it mostly works. It is robust to some extent, but it doesn't always work. Like 95%, let's say it works. The long tail is what we always work on. So yeah, actually, we can maybe like if you have time, we can go for we can see the domain randomization sim to real transfer. It's a very hot topic right now. So there is so much going on.
There is a
But
question.
yeah, for Slam and for everything, it will work. It is robust to some extent, but you will have to will have to implement all these techniques like
So if I understand, if we could train the mobile robot and
yeah.
create something like an SDK, so it knows how to traverse given these different physical situations through RL. The rest of the
Yes.
things maybe we have to do through a control, algorithm, like a deterministic, where you are manipulating the whole thing. It's not like I can just somehow RL the robot to run around in my whole house by itself. I cannot train like that, I guess, right? Because in the house, everything is moving
Yeah.
all the time. People are walking
Yeah.
around. The furniture may not be in the same place
Right.
and things
Right.
like that. So the
Yeah. Yeah. Yeah.
basics may be
So
RL, and then
yeah.
you still have to learn how to program.
Yeah. 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 So what you're saying is RL is sort of a replacement for the controller, but
Yeah, that
still,
was my dream. That
the
would have been
yeah, yeah.
amazing.
Hmm.
So RL is a replacement for the controller, and the whatever the control commands that comes from RL algorithm, RL policy, that will be used as nominal control policy, and then we have classical controls around it to make it robust or take into account all this uncertainties in the environment. So yeah, what you're proposing is yeah, that people do that actually. Yeah, if you look for this tube MPC, it's called model predictive control or maybe robust MPC. These are the techniques. Like the controller can be anything. RLE can be the controller, and then we'll have more fine control on top of it.
Can you type those names in the chat, please? I'll copy. Thanks.
Sorry, Rajesh, actually your voice broke.
No. The names, what you said, that I didn't pick up easily. So if you could just type that,
Okay.
what I have to research.
Okay, sure.
Thanks.
I'll type it here.
Okay, so there is a question on the chat about how VLAs are trained. So if you look at the training of Pi 0.5, they have two phases. The first is the pre-training and the second is the post-training. And in the pre-training, they use a lot of data. So they have this mobile manipulator data, multi-environment, non-mobile robot data, cross-embodiment laboratory data, and two or three more other modes. So most of these data sets are robots performing tasks, and then these are wide range of tasks which the robot is performing. And in some papers, I have seen there are simulation data also used in the pre-training phase, but largely it is robots performing real life tasks. For example, if you look at the first VLA developed by Google, which was RT1, in that the pre-training the data set which they used for pre-training was a robot which was moving around in a kitchen environment for a year and doing a lot of tasks, and the data was collected and that was used to pre-train RT1. And then in the post-training phase, it is more like fine-tuning for some domain-specific tasks. Like let's say if you want to fold clothes, maybe the robot has already seen some demonstration of folding clothes, so you don't have to train it on a lot of or fine-tune it on a lot of episodes in the post-training phase. Yeah, so this is how VLAs are trained. Question is about behavior challenge. Yes, that is only simulation. Here they have nothing about real world. And if you look at the success rate also, this was Ilia's team, and they don't get a very high success rate. It's almost around hovering around 12 to 15% across tasks. And the reason it appears somewhat less is out of 50 tasks, in 22 tasks, it's almost 80 to 90%. But there are some tasks where the robot gets a very bad accuracy. It's not able to do the task at all. So that's why the overall accuracy drops. But yeah, this is completely in simulation. They have no intention of doing this in real robots, and that's what I see in most of these simulation challenges which have been released publicly. Okay, let's move ahead. And so this is something which we are not going to look at right now. They have a tool where you can actually do teleoperation and you can control this arm to do pick and place and collect trajectories. So they have a simple, using a mouse control, you can move the end effector, you can pick the red cube and you can place it on top of the green cube. So these are the recordings or the data set which we use to train our policy. In today's lecture, we are going to use a data set which is already available in Maniskill, so we are not going to do the teleoperation from scratch. Okay, now let's go to the next part, which is very interesting. So as I said before, we are going to now learn how to implement a policy within the agent environment interface in Gymnasium. And for that, we are going to use the proximal policy optimization. So if you are following this notebook, just click on this link, which is the second code cell. You can just run it, and it will run two files, which is ppo.py and ppo_rgb.py. So this is where the training logic using reinforcement learning is written, and at the bottom we'll just run this. This is tensor board. So once we train our RL policy, you can see the reward curves and how they vary. ideally we want the rewards to rise with time, which means that our policy is learning from interactions with the environment. Okay, so the first is the based RL. So what state-based RL means is it is not looking at the observations from the cameras. At every time step, initially the robot starts by taking random actions and then it gets rewards. Uh, Now, these rewards are defined within this PPO.py function, but most probably these are going to be sparse rewards which you are getting at the end of your trajectory. So let's say this is push cube. So if you manage to push the cube successfully, then you will get a plus reward or you get a negative reward. And the way proximal policy optimization works is it's very similar to what I mentioned before. If a trajectory gets a high reward or a positive reward, you reinforce all the actions which are taken in the trajectory and vice versa if the trajectory gets a negative reward. So just run this cell. So the RL training is very simple because of this. It's just like one single line where you have to mention the environment ID. The number of environments is 1024 here. So it's simulating in all these environments parallelly, and it's learning from implementations in all of these environments at the same time. And it doesn't take much time for this to run, so I'll just maybe wait till it starts running. We will see. For RL, we don't need any demonstrations, Vishnu. It is mostly through trial and error. So for every observation, we perform an action, and initially we start with actions which are random. But then slowly, as we start to accumulate rewards, the robot starts to become smarter. It starts to learn, okay, this is what I should do, this is what I shouldn't do. And initially, since the movements are so random, it might happen that for the first 100, 200 episodes, you don't get any reward signal at all. That's why the initial idea which we discussed of training with imitation learning and then doing RL makes a lot of sense, because then initially you will immediately start with at least some positive reward. But here it takes a long time before you get the first reward. So this should ideally start to show some training signals, but it's taking a bit of a time. Let me wait for a minute and see.
Rajat, do you know if we can manipulate reward functions inside the environment or
Uh,
Maniskill?
I have not tried that, but it should be possible. My guess is that you would have to look into the ppo.py file.
Okay,
Within that, we will need to modify the reward functions.
got it.
Yeah. Yeah. So the question in the chat is interesting. How is the reward converted such that it can update the model weights? So, okay, maybe let me just try to see if I can explain this in a simple way. So I have written one article on this, which is policy gradient methods. Okay, so Okay, so this is slightly an involved topic, but let me try to explain it so that all of us understand it. So first of all, the policy which is used is parameterized as a neural network. So what the policy essentially gives is, for every state which is denoted by ST, what is the probability of taking an action AT? Let's take an example of the SO101 arm with 6 degrees of freedom. In that case, we have 6 possible actions as an output. And for every state, our probability, this function will tell me a probability distribution across these 6 actions. So maybe action number 1 will have a probability of uh, maybe zero point 0.1, then the second action will have a probability of 0.2, etc. And whichever action has the highest probability, your robot will pick that action for that observation. Okay, so this is the most important notation, which is denoted by pi. And pi of AT given ST means for that given observation, what is the probability distribution across all possible actions. Now, somehow intuitively we understand that once we get a reward, we need to update this pi function, because finally everything is embedded here. So more specifically, how we want to update this is, if I get a very high reward, then the probability of this action which was taken in the trajectory should be increased. If I get a low reward, the probability should be decreased, right? Now, the way that is done is, let's say initially your policy theta 1, theta 2 was represented by this red vector. This red vector indicates this is the probability of taking a specific action given a state. Let's focus on one action now. Let's call it A1 given S1. Now, if the reward is positive, I need it to I need to add a green vector to this red vector so that finally I get a blue vector out of it. Now, why is the blue vector better compared to the red vector? Because the blue vector is more higher up on the mountain compared to the red vector. The red vector is towards the base, the blue vector is more towards the peak. What does towards the peak mean? It means it has a higher probability of getting chosen now. Now, what the policy gradient method or PPO does is, it calculates this green vector very smartly. And this green vector is represented by this formula, which is gradient of log of this policy into G, where G is the reward. Now, you see this is directly proportional. So if G is positive, you are going to go towards the mountain. If G is negative, you will go towards the base, which makes sense, right? If you get a very bad reward, you need to reduce the probability of picking that action. So this is how the probability of those actions are reinforced or increased. When I say reinforced, I mean the probability is increased. You want to pick those actions more and more in the trajectory. If the reward is less, you need to move the probability back towards the base so that the chances of picking that action is reduced. And that is done using this formula, which is also called as a policy gradient method. And there are so many variations in the policy gradient methods. The PPO is one, then GRPO, which DeepSeek introduced, that is another variation. All of these are minor tweaks, but the first policy gradient method was developed by Richard Sutton's group in, I think, 1999 or something, which is now called as vanilla policy gradient. But everything else is built on top of this intuition only. Okay, I hope this is clear. This is exactly what is happening here underneath. I am not sure why this is taking a lot of time. Is anyone able to run this successfully? So this worked for me the previous 2 3 times I ran this, but today for some reason it is uh, I think I might need to change the.
No, for me it works, but I don't know how to share. Yeah, it has come for you. Same video.
Okay, okay. Actually, this was present before also.
Oh, okay.
I see some red sign over here at the top. Think this is disconnected. Okay. Uh, okay, fine. So at the end, right, when this runs, you should see this video where you can see these 8 parallel environments. Uh, just change the run type. Need to run this again. Num environments 5 and 2 works. We have got a message in the chat. Let me try with that. Okay, let's go down and run it again.
I changed it to A100. It is working for me now. It is training.
Okay, great. Let me check with this 5 and 2 environments. Okay, it has started the training now. Now just observe this reward, okay? That's the most important metric we need to track. So evaluation reward mean initially is 0.07. So I want this to increase at every epoch. This means that the robot is actually learning, otherwise you are not learning anything. Reward mean is 0.2. So this has definitely increased by more than 3 times, I guess. Okay, the reward is now consistently increasing. It might go beyond 1. Let's see what our tensor board says. So we have to run till 6 lakh steps. Let's see. We're almost there. So here on the left, if you click on this folder sign, And if you click on runs and state push cube, you will see that it saves videos 0, 1, 2, 3, 4, 5. And the initial videos might not work well, but as you proceed towards the latter videos, it will be able to uh, do the task properly. Now, what is the task here? I'll show you in a while, but there is a there is a target which is marked on the table, and the task for the robot is to push the cube so that it moves and lands within the target. Only when it does that, it will get a positive reward, otherwise it will get a reward of 0. And the meaning of in this reward increase is that it's able to successfully move the cube towards the center of the target. Yeah, now you can see these tensor board curves evolve. Let's see, where is the okay, yeah, this is the reward. So almost it's increasing till point 8, then it stagnates, and it's, I think, again going down. So maybe checkpoint 4 lakh is the best, which has the highest reward. So let's do one thing. This is completed now. Let's do 0.mp4 and see the video at the first. So you see, it's very poor. It's not even doing anything. It's just closing the gripper. Now let's change it to 1. Let's see what it does now. Kind of better. It's picking it, but still not moving to the target. So it's learning through trial and error. And if you go change it to 2, you see it learns to push it. Again, it's not pushing towards the center, but it's pushing it. And if you do 3, I think it will place it exactly towards the center. Yeah. Now, as we saw, the reward has dropped at 4. So at 4, I'm not expecting a significantly better performance, but still decent, I think. Some of these are moving beyond the center, but overall, it's not bad. So this is something which is very satisfying to see. Whenever I see a reward curve increase in RL, I get a sense of satisfaction, because teaching something through trial and error is very different than teaching something through imitation learning. Trial and error somehow feels that it's more scalable and generalizable, because the robot is learning something through its own experience, which is what humans do. We don't just look at 100 trajectories and learn from them, but we experience in the world directly out there, and we improve upon it based on whatever experience we are getting. So this is very fascinating. I encourage all of you to experiment more with the reward functions also in this file, and try with more different environments as well. Now the next is visual based RL. This takes a bit of a time, and I will not run this now because it doesn't teach anything significantly new. It's just that it's more accurate compared to state based RL, but the process remains exactly the same. Maybe if yeah, this is one of the video of. Now the reason you are getting these blurry images over here is because it is something which is recorded through the camera, which is inside the simulation environment. So it appears a little bit pixelated because it's the replay taken from the camera perspective. Okay, now we come to the next step, which is imitation learning. We have covered RL, and now we are moving to imitation learning. As we have seen throughout this bootcamp, we have largely focused on imitation learning only. So RL might have been somewhat fresh to all of you, but it's a very interesting field, as you just saw how our agent was learning with time. But in imitation learning, what happens is that we have to collect a lot of data, and they have a function called utils.download_demo, where they already have a lot of demos for each tasks. So this is for peg insertion. It is downloading demonstrations. And I think there are 1,000 trajectories inside each demo. So we will look at that in more detail. So we'll just play one sample so you can see how it picks the peg and inserts it in the cube. This is the peg insertion task which we want to train the agent on. So yeah, here it's just explaining more about the different items in the data set and the trajectory. So one thing you can see is where is the data saved. If you go to folder and go to demos, here we have this peg insertion dash v1, and here you have two different folders, motion planning and RL. So in imitation learning, we are going to use this trajectory.h5. Now, what does the trajectory.h5 contain? It contains every single observation at each time step. Very similar to the data which we store on Hugging Face, right? After we record the episodes. This is what the trajectory.h5 contains. So that is the file which we need to train our policy on. Okay, this is just, I think, can load the data set and see what it is. So I'll just run these. This is not very important. It explains the different items which are loaded in the trajectories. Now, the important thing is these raw trajectories, they do not include actual observations because the observation mode is set to state only. Uh, so to convert these observations to observations which include the robot positions as well as the camera images, we need to use a function called trajectory replay. I think they might have explained it here. So we are going to look at this when we train our act policy. This is a bit, they have given a lot of code here, but I think all of this is, they have a simple function. Instead of writing this replay function from scratch, we can use a simple function from Maniskill, which I will explain in a while. Yeah, so let's first run this. This was the function I was talking about, which is written over here. It's called replay trajectory. And here what do we have to do is, this is the trajectory which is saved in our demos folder. We simply have to give observation mode as RGBD. So it will take the same trajectory and it will convert uh, the trajectories by including the observations as well. So here you can see this, the demonstration dataset does not include actual observations in order to save space. And you can convert trajectories to the desired option, observation and action space, and specify the number of parallel processes to run to speed this up. So this is exactly what we have done here. It is called as replay trajectory. So there are two functions which we have looked at in the imitation learning domain. The first is this function, which is downloading the dataset over here, download demo. After this, we didn't really look at all of this in detail, but the next important step for us was to understand this function, which is replaying the trajectories to convert the observation mode from state only to state plus RGBD, which is the images recorded by your cameras. Okay, now we can just play this and let's see. Okay, maybe I did not run this. So this number of processors is no longer a recognized argument, so you can remove it from the code. So you see here it says replaying trajectory 0, which means that it is converting the trajectory 0. And then now it says replaying trajectory 1, which means that it is converting trajectory 1. And why it is converting only two trajectories is because I have given count as 2 over here. Okay, so the count has been given 2, so it is converting only two trajectories. But in reality, as I said, there are 1,000 trajectories which we will download and we'll convert all those 1,000 trajectories. Now, this is something, let's see. Okay, so we are converting these demonstrations now, and this is something which is not really important, so I can skip this. Okay, let's skip this part. And the next part they have mentioned here is heterogeneous simulation, and I think that's almost the end of this. They have some other uh, features also. So for now, what we'll do is we will stick with this demonstration data section. And as I said, the main aim of today's lecture is to train uh, an ACT policy to learn from our demonstration data set. So we will be using this download demo function and the replay trajectories function as well. So what we'll do is let us take a break for 2 minutes. I think we are already into 2 hours, but I think this last part is very important for all of us to learn because it will provide some sort of completion to this bootcamp because we have covered with the real data set. Now it will make a lot of sense if we simulate the ACT policy on the simulated data set also. So I will take a small break for 2 minutes and then we will be back. Okay, let us begin this last part of today's lecture now. So, firstly, before we start, there is a GitHub repo which we have created for all of you to replicate this. Let's see. Yeah, this is the GitHub repo. I will share this in the chat. All of you, please open this GitHub repo. And we are going to use the runpod environment for training our ACT policy. Initially, I had done this using my own laptop, but it takes a lot of time to train on the trajectories that we have downloaded, so it is not at all efficient. Now, in this course, I have already taught how to open up pods in RunPod, and I have gone to RunPod and I have used this particular pod. Now, this is RTX 4090, which is costing me around $0.5 per hour. And I've increased the disk size of this to 50 GB because we are downloading a lot of trajectories. And I think by now all of you will be comfortable. You can either open this in Jupyter Notebook or you can connect it through Google through VS Code using SSH. So to do that, you will need this port ID and this number also, IP address and the port ID you will need. And then you can successfully connect this through your VS Code, which I find to be very convenient. So I will directly assume you know all of this, and I will head over to the workspace. It is completely clean right now, as you can see. So I'll start by cloning this repo first. Let's go to this, click on this and say git clone. Okay, so the repo is cloned. Now I'll move to the folder act Maniskill. Now we have created this setup Maniskill file for all of you. The reason we have created this is because setting up Maniskill on RunPod is slightly more challenging compared to your own local PC. This is because we have to do some changes with the drivers. They use this Vulkan drivers for rendering graphics, and these Vulkan drivers are not directly available with RunPods. So you need to do some changes in your settings. But if you just run this file, everything will be done for you. So just do bash setup underscore maniskill.sh. And you can see here it starts with updating system packages, installing Vulkan dependencies, and then it directly moves on to installing Maniskill and its dependencies. Now, once all these checkpoints are completed, you will get a message saying that Maniskill has been installed successfully. Once that happens, it means that you are good to go with the setup. The main issues that we faced before we created this setup file was that it, remember I said before you need to replay the trajectories to convert the state observations into state plus images observations. That is not easy in the RunPod. It's not straightforward and there is no documentation available as to how to do that. You might think that, okay, why not do it in my local PC? You can do that. The only thing is the training will take a huge amount of time in that case. Okay, now what I'm going to do is I'm going to click on this second file, which is Maniskill official replay. Now here I'm going to explain what all things we are going to do. As I said, the first step is to download the demo data. So I'll just click this. Okay, I need to enable this Python plus Jupyter extension. So I will do that. And we will download this demonstration dataset, which is pick cube v1. What will this demonstration dataset do? It will pick up the red cube and place it on the green sphere, and there will be 1,000 successful trajectories. So let me just play this again. Okay, this is okay. Ideally, they should just start here right now. I'm not sure why this is. Okay, so what I will do is let's skip this step and go to the train act sh. in which we are again doing the same things in a step-by-step manner. So go to this and click on type bash train underscore act.sh. So once you do that, the first thing it will do is it will clone this Maniskill repository, which is the official Maniskill repository. Here you can see this is the first step out of the 8 steps. And whatever I was about to display here was just to download the trajectories and replay the trajectories to convert the state observations to RGBD. And I think that is included in this automatically. So I hope that works. Now it asks for the weights and biases setup, which I definitely want. So, okay, let me quickly get my key and enter it over here. Okay, I have entered my key. Now, yeah, here you can see after I entered my key, we entered the third step, which is downloading demo trajectories. So it downloaded 1,000 trajectories uh, for the pick and place task. Now here it asks select number of demos for training. So ideally I should use 1,000 trajectories, but for now, since we are delivering this class, I'll select 100. And total, so far what we have done is we have picked 100 trajectories which we are going to use for training the ACT policy. The total training iterations, let me click 30,000, and evaluation frequency is 5,000. Maximum episode steps, let's say 125. And so this one takes time because after every, let's say, 5,000 episodes, I have mentioned my evaluation frequency as 5,000, which means after 5,000 episodes, it will evaluate whether my policy is performing right or wrong. That usually takes some amount of time because it has to calculate the success rate if it is picking the cube and placing it correctly or not. Now, how is the success rate defined? There are two types of success. First is success at the start, whether it is picking the cube correctly. The second is success at the end, whether it is placing the red cube on the sphere correctly or not. So let me say episodes per evaluation is 100. Parallel environment, let's keep it 1. If we increase the number of parallel environments, it runs into some errors according to our observations. So we'll keep it as 1. Now you see the next step is the most important, which is replaying trajectories. And here it will replay 100 trajectories. The code which we have written will be somewhere over here. Yeah, in the replay trajectories, all we are doing is we are mentioning this output mode as RGBD, that's all. So whatever 1,000 trajectories we had downloaded, the same trajectories, the 100 of those trajectories will be considered since we selected 100 as the number before. And it will replay all those 100 trajectories by changing the observation mode to RGBD. Now, after this, we have the exact same setup which we did in real. What we did was we recorded episodes, right? And we saved the images using our camera. Same thing now we are doing where the episodes are already recorded and the images are now saved using this replay trajectory function. So after this class is done, I would encourage all of you to do this same uh, pattern and replicate this for 1,000 trajectories so that you will get an even better accuracy. Okay, so the replaying is done. Now the actual training is starting. So you might be wondering what is happening in this training. Remember, we cloned this Maniskill repo. Inside this Maniskill repo, if you go, there is a folder called examples. Within that, there is a folder called baselines, and there is a folder called act. And we want this file train underscore rgvd.py. Now, this is the exact file which we are going to run here. This code will be run. So here you can see training devices RTX 4090, PQ1, RGBD data, number of demos 100, evaluation frequency is 5000. After every 5000, it will give me my reward and success rate. And ideally, I want my success rate to keep on increasing as the training proceeds, which means I'm doing fine. So let's start the training. The question is, are we using the same 100 episodes? So what we are doing is, yes, we are using the 100 episodes, but uh, we are using the entire 100 episodes for training. And for evaluation, we are using a different set of episodes. We are not using the same episodes. For evaluation, we are placing the cube uh, randomly, and we are checking whether it's able to pick and place it correctly or not. So otherwise, if we use the uh, same episodes cannot be used for evaluation, because in the training episodes, it's anyways picking and placing correctly. So in the evaluation, we are using a different set of episodes to make sure that the robot is working well in scenarios which are different than what are encountered during the training. So the question is, how do we measure the uh, success rate for evaluation? So let me explain that using one example. So I'll be posting this as an article also in some time. Okay, so let's take an example of okay, so this is one evaluation episode where you can see it is placing the red, and it is picking the red cube and placing it on the green sphere, which is what we want. So it says success 1 at the start because that's what we are expecting. But if you look at the second one also has a success 1. Third one, let's see. Yeah, this is in fact the videos we get after our policy is trained. So this was the final thing which I wanted to show you. So these are all the episodes which have worked out to be fine actually. Yeah, here it didn't pick it up, see. So we it messes it up. So it gets a reward of success of 0. So after every 5000 steps, this is what we are evaluating. And we can see maybe if the training has started or not over here. Let us see in the our dashboard the training has started. So it has not yet started the training. I think it is still loading the data set. So till that time, let me show you the final curves that we get once this simulation is complete. So this is the one I got yesterday when I ran this. So here you see there are two things. First is success once and success at the end. Success once means it will just say whether the cube has been picked or not at the start. And success at the end means whether the cube has been placed at the end or not. So first observation, you can see that success once in the evaluation, right? It's pretty high. It's actually more than 0.7, I think. But success at the end is somewhere around 63%, if I'm not wrong. So it means that majority of the times it is first of all improving with time, which is a great sign. Our model is actually working and it's learning to pick and place the cube. But the success at once, it is picking the cube more often than placing the cube correctly. So that is what we can generally evaluate, or we can infer from these evaluation curves. Let's look at our training and see how far it has gone ahead. Still says downloading ResNet 18. Remember, we had ResNet 18 in the Act policy where the images were first converted into feature maps and then tokenized and passed through the transformer encoder and decoder. It's basically the same thing we are doing, but now through our simulation data over here. Yeah, so the question is that why is there a reward? So this is imitation learning, so ideally we should not use the reward word. I'm not completely sure what this reward means actually, but it is something which is used as a proxy for whether it's able to pick and place the cube correctly or not. It does not mean we are doing reinforcement learning, but it is some function of whether we are picking and placing the cube correctly. So we will actually see what this reward means once we get through the first 5,000 evaluation steps. We can see it here at the bottom in the logs. We can see it in our terminal. Can all of you just run this and see whether anyone has the training started for anyone? Okay, so you see here initially when it started out, after 100 episodes, the success once rate is 0.02 and success end is also 0.02, which means for 2 out of 100 episodes it worked fine. and the return, this doesn't make much sense. So let's just focus on the success rate. Now the next evaluation will be done after 5,000 episodes, and we have already seen how the curve rises. So initially it works only for 2 out of 100 episodes, but then as we are training it, it's slowly learning, and the success rate will improve with time. So please try this out. All of you, you can clone this repo. We have already curated all the instructions for you. And there is a lot to explore in this simulation environment of Maniskill. So the sky is the limit, really. But I wanted to explain to you how accessible this is for beginners. So that's why I really liked the Maniskill framework. And just one last thing before sim to real. So there is a tutorial on sim to real where it has been explained how to transfer policies from simulations to real. Let me check where that is. Yeah, here. So please have a look at this tutorial, which explains all the details on how to transfer the simulation policy to reality. So this is how it works at the end. So it's just learning to pick up the cue.
But as you said, this is for SO
This is
100
for
again.
SO 100. Yes, yes. This is for SO 100. Um, so some tweaks have to be made over here to, as you see over here at the end. Note that while SO101 looks similar, we have found that there are some key differences that make sim2real fail for SO101. So we will update this repository. So they have not yet updated it. They have said that they will update it, but they have not yet updated it.